Welcome to AP Biology. This video is on the chemical context of life. The elements and molecules that we discuss in this chapter are the building blocks that all life is composed of. What is an element? An element is a substance that cannot be broken down into other substances by chemical reactions. There are 92 total elements on the periodic table. There are 25 elements that are needed for life. 96% of all living matter is made up of 4 elements: carbon, hydrogen, oxygen, and nitrogen. We also see other elements that are found in smaller quantities. Some of the other elements that are found in smaller quantities in living organisms are elements like calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. We will see all these elements during the course of AP Biology. There are other elements that are trace elements. They're required in much smaller amounts. A lot of these are minerals like iron and fluorine and copper and cobalt, manganese. These are used, or they're needed in very, very, very small concentrations. They add up to 0.01% of body mass. A substance that contains 2 or more elements found in a fixed ratio is called a compound. Here on the bottom we see an example of a compound. Here on the left we see sodium. Here on the right we see chlorine. Sodium and chlorine together make sodium chloride, which is a compound, and it's what we commonly call table salt. Some elements can be toxic. They could be harmful to an organism, and some species adapted tolerance to these toxic elements. An example of this is a plant community that has become tolerant to the toxic element serpentine. A toxic element called serpentine is found in the soil, is normally harmful to organisms, can harm them or kill them, and you can see that all the plant species that live in this environment, like this flower you see right here, have adapted over time to become tolerant to the toxin. And we'll discuss throughout this course how organisms build tolerance to various elements and compounds. What gives an element its properties? What makes an element an element? What makes it what it is? An atom is the smallest particle of an element. There are some elements like oxygen that are diatomic. They're composed of 2 atoms bonded together. For instance, oxygen is found as O2. An atom is made up of protons, neutrons, and electrons. The nucleus of the atom is made up of protons and neutrons, and revolving around the nucleus, or orbiting the nucleus, are going to be the electrons. The atomic number of an atom is the number of protons. The atomic number, or the number of protons, is what designates an atom as to what type of atom it is. For instance, carbon has an atomic number of 12. It has 12 protons. Also in the nucleus we find neutrons. The number of neutrons does not always have to equal the number of protons. The number of electrons that orbit the nucleus, though, the number of electrons do equal the number of protons. To determine the atomic mass of an atom, we add up the protons and the neutrons, giving us the atomic mass. The reason why we don't include the electrons is because they have a negligible mass. So the atomic number is the number of protons. The atomic mass is the protons plus the neutrons. Throughout AP Biology, we're going to discuss many different isotopes. Isotopes are different atoms of the same element. They have the same number of protons because they're the same element, but they have a different number of neutrons. So they have the same atomic number, but they have a different atomic mass. Some of these isotopes are radioactive. To be radioactive means that the nucleus decays. In particular, the neutrons break down and it releases energy. The protons don't break down. If they broke down, it would actually turn into a different element. These radioactive isotopes are used for many applications in biology. One thing that they're used for is dating fossils. A common radioactive isotope used to date fossils is called carbon-14. We call this carbon dating. Carbon-14 is the radioactive isotope of carbon-12. Carbon-14 decays at a known rate, and we can look at the amount of carbon-14 in an organism versus the amount of carbon-12 to tell how old it is. Radioactive isotopes are also used to trace atoms through metabolic processes and to diagnose medical disorders. A radioactive isotope can be injected into an individual. We call this a radioactive tracer. An example of a common radioactive tracer is an isotope of glucose. It's a radioactive isotope of glucose. And this is often used to diagnose cancer, in particular to see if cancer metastasized and traveled throughout the body and established itself somewhere else. What we do is we inject the individual with a form of radioactive glucose. Cancer cells absorb or take in a huge amount of glucose. So this glucose that has been injected into the body that is radioactive is going to travel to all the cancer cells that are then going to take it in. This radioactive glucose gives off energy, and a particular type of scan called a PET scan picks up that energy and can be used to find tumors throughout the body. Here we see an example of cancerous throat tissue that has been discovered, has been found using a PET scan and a radioactive isotope of glucose. The electrons are a really important part of the atom in terms of this course. The amount of energy that an electron has depends on how close or how far it is from the nucleus. The further away an electron is from the nucleus, which you can see here, the more potential energy that it has. Electrons are going to be a really important part of this course because the electrons are the part of the atom that participates in chemical reactions, making or breaking chemical bonds. There are multiple energy levels or electron shells that electrons can be found in. The first electron shell, which is closest to the nucleus, can hold a total of 2 electrons. The second electron shell can hold a maximum of 8 electrons, and the third electron shell can hold a maximum of 8 electrons as well. The way that atoms react chemically is determined by the number and the arrangement of the electrons. The outermost electron shell that contains electrons is called the valence shell. Those electrons in the valence shell are called valence electrons. Atoms react with each other in order to fill up their valence shell. When their valence shell is full, an atom is happy and it is unreactive. Atoms are reactive when their valence shell is not filled. So if you're looking at this section of the periodic table, you can see that there are some gases here that we call inert gases. They're not reactive, like helium, like neon, like argon. And the reason why these gases are not reactive is because their valence shell is full. If you look at atoms like oxygen, like fluorine, right, like chlorine, like sulfur, these atoms are extremely reactive because their valence shells are not full. What makes them very reactive is that they do not require many electrons, or they do not have to lose many electrons to complete their valence shell. So atoms are going to react with one another in order to fill their valence shell. When atoms react, they form bonds. And these bonds are formed in order to complete their valence shells. Bonds can be formed by different means, though. There are different types of bonds that can form. A molecule is any particle that consists of two or more atoms held together by chemical bonds. The difference between a molecule and a compound is that a compound has to be made up of two or more different atoms, but a molecule is anything made up of two or more atoms. So for instance, O2, it's an element because it's just made up of oxygen, but it's also a molecule because it's made up of two oxygens put together. The first type of bond that can form is called an ionic bond. An ionic bond is the result of a mutual attraction of ions. Ions are charged atoms or molecules. There are two types of ions. You have a cation that has a positive charge and an anion that has a negative charge. Ions are formed as the result of atoms gaining or losing electrons. Here we see a common ionic bond that takes place between sodium and chlorine. If we look at sodium, sodium has a valence of 1. It has one valence electron. If you look at chlorine, it has a valence of 7. It has 7 valence electrons. The easiest way for both of these atoms to complete their valence shells is for the electron to move from sodium to chlorine. So sodium is going to lose an electron, chlorine is going to gain an electron. Electrons have negative charges. So sodium loses a negative charge, therefore it gains a positive charge. It becomes what we call a cation, a positively charged atom. The reason why it becomes positively charged is because atoms have the same number of protons as electrons. Protons have positive charge, electrons have a negative charge. Therefore, since you have an equal number of positives and negatives, the atom as a whole is neutral. But when you lose a negatively charged electron, sodium now has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 protons in the nucleus, so 11 positive charges, but only 10 negative charges. So it has a positive charge we call a cation. The chlorine is going to gain the electron. It gains a negative charge, and we call it an anion. Now this positive atom, this positive ion I should say, is going to stick to the negative ion, just like opposite sides of a magnet are attracted to each other. And this attraction, this sticking together of these two ions, is what we call an ionic bond. An ionic bond is a strong bond. The second type of bond is a covalent bond. The covalent bond is the result of sharing electrons. So in this case, the best way to fill the valence shells is not to transfer electrons, but to share them. You can have a single covalent bond if one pair of electrons is shared. You can have a double covalent bond if two pairs of electrons are shared. Covalent bonds can be polar or nonpolar. A polar covalent bond is going to be caused by an atom having electronegativity. An electronegative atom pulls electrons in close to it. It has a strong pull of electrons. If we go back to our periodic table, you can see that some atoms that have a very high electronegativity are going to be oxygen, you're going to be fluorine, nitrogen is also electronegative, right? In particular, we're going to see often in this course oxygen, right? Oxygen is an extremely electronegative atom. These atoms pull electrons in close to it, and you can see why they would do that. They want to complete their valence shells by gaining those electrons. Non-polar covalent bonds are the result of equal sharing of electrons. You don't have an electronegative atom, therefore electrons do not get pulled in close to it. All the electrons are shared equally. Some example of non-polar covalent bonds would be like hydrogen here, H2. This is methane, CH4. Contains all non-polar covalent bonds. Covalent bonds, electrons are being shared. Non-polar because they're being shared equally. Carbon and hydrogen are both not electronegative. They don't pull electrons in close to them. When you see molecules that are made up of oxygen or nitrogen, many of these molecules are polar. They contain polar covalent bonds because they contain electronegative atoms. And these electronegative atoms pull electrons in close to them, so you have an unequal sharing of the electrons. You have a distribution of charge, a difference in charge, that we call this polar covalent bond. I'm going to fast forward a little bit. I'm going to show you oxygen and hydrogen forming water. Alright, so water is H2O, and water is a polar molecule. The reason why it's polar is because oxygen is electronegative. So oxygen is going to pull hydrogen's electrons in close to it because of its electronegativity. As a result, oxygen gains a partially negative charge, hydrogen gains a partially positive charge. There's a distribution of charge here. This covalent bond right here and right here, these are polar covalent bonds. They have an unequal sharing of the electrons. All the electrons are hanging out by oxygen. These polar covalent bonds make water a polar molecule. A molecule that has this distribution of charge. When polar molecules are next to each other, this can cause hydrogen bonds to form. Both covalent bonds and ionic bonds are strong bonds. A hydrogen bond is a weak bond, although we'll see soon that collectively it can create a strong force. So when you have two polar molecules next to each other, here we have water and we have ammonia. If you look at the water molecule, the hydrogen has a partially positive charge, and we usually draw partial at this symbol right here. If you look at nitrogen, nitrogen is going to have a partially negative charge because it's electronegative. And the partially positive hydrogen of one molecule is being attracted to the partial negative charge of another molecule. Just like in the ionic bond, positive charge is attracted to negative charge, and this bond that results is called a hydrogen bond. It's weaker than the ionic bond because the ionic bond has a positive charge and a negative charge being attracted, and the hydrogen bond you have a partial positive and a partial negative attracted to one another. So here you see a hydrogen bond, and we're going to see these bonds very often in AP biology. Another type of weak interaction, weak bond, is called van der Waals interactions. These are the result of partially different charges being attracted to one another. They're not necessarily hydrogen bonds, but it's a weak attraction that results from differently charged molecules being attracted to one another. A good example of a van der Waals interaction is found on a gecko's toe hairs. If you look at the bottom of a gecko's hand and foot, they have an extreme amount of surface area. All these bumps and grooves, all these folds that increase surface area, and the surface is covered by hair. And these hairs contain all kinds of weak charges. There are weak positive charges, there are weak negative charges all over the place. When a gecko tries to climb something like a piece of glass or like a wall, all the partial charges on its hands and feet are attracted to all the partial charges that are on the glass or on the wall. These interactions, sticking the two together, are called van der Waals interactions. And again, individually, each interaction is very weak, but you can see it can form a collectively strong grip. Collectively, it could be a strong force. Chemical reactions involve the making and the breaking of chemical bonds, and this is going to lead to a change in the composition of matter. When you look at a chemical reaction, you have the reactant going into the reaction and the product coming out. All reactions are reversible. All chemical reactions can go in both directions. Chemical equilibrium is going to be when a chemical reaction effectively ends. All the reactants are not converted into products. That's not when a chemical reaction ends. But when there is no net effect on the concentration of reactants and products. This is because the reactions are reversible. They go in both directions. When the net change stays the same, right? When you don't have any change in reactants or products over a given period of time, we say that that chemical reaction is in chemical equilibrium. It does not mean that the reactants and products are equal in concentration, just that they are no longer changing. So during the course of AP Biology, we're going to be looking at different molecules and what the function of these molecules are. And this is a really important lesson. The relationship between structure and function, or you could say the relationship between shape and function. The structure of a molecule, the shape of a molecule, is going to determine what that molecule is able to do. It's going to determine that molecule's function. When chemical bonds form, it creates these molecules that have unique shapes to them. And the shape of that molecule, again, dictates the function. I know I'm being very repetitive. An example here is with a molecule called a neurotransmitter, which is used in the nervous system, and it's how one neuron communicates with another neuron. They communicate by releasing chemicals called neurotransmitters that are going to bind to receptors on the neuron. Whether or not the neurotransmitter can bind to the receptor is dependent upon the structure of that neurotransmitter. Just a slight change in the neurotransmitter structure can make it unable to bind to the receptor, and you would lose the ability to communicate. So the shape of the molecule, the structure of the neurotransmitter, is absolutely crucial to its functioning. We're going to see this theme of the relationship between structure and function throughout this entire course. This completes our lesson.